n into x cap of n into ts. Okay, the difference between the two, that is x of n into ts, and its predicted value or its approximation is e of n into ts. Now, if the predictor is very good, then e of n into ts will be very, very small, and this difference will be quantized, and the quantized output will be fed back to the prediction filter so that it can predict for the next incoming sample. And this quantized level is encoded depending on the number of bits or number of bits required for the representation level, right? So this will lead to a study of transmitter of DPCM, right? What is the analysis here? So V of n into Ts, you can see the output of the quantizer is nothing but quantization of E of n into Ts. E of n into Ts is prediction error. We call it as a prediction error, E of n into Ts, which is nothing but V of n into Ts is nothing but E of n into Ts plus Q of n into Ts. This E of n into Ts is a prediction error. Q of n into Ts is a quantization error, right? Which is again very, very small, right? So E of n into Ts is a prediction error. Q of n into Ts is a quantization error, right? So resulting signal is a V of n into Ts. Resulting sample will be V of n into Ts, which quantizes the prediction error, right? So this output V of n into Ts is fed to the adder along with the prediction filter output. So the prediction filter output is fed to the adder here. Now the output of this adder is nothing but U of n into Ts. Now what is this U of n into Ts? U of n into Ts is the predicted output of the prediction filter, right? Predicted value of the present sample, that is x cap of n into Ts plus V of n into Ts. V of n into Ts is the quantizer output, right? Now U of n into Ts, again I can say this as x cap of n into Ts because it is added, right? So x cap of n into Ts plus V of n into Ts is nothing but E of n into Ts plus Q of n into Ts, right? So E of n into Ts plus Q of n into Ts. Now what this x cap of n into Ts plus E of n into Ts, we know this E of n into Ts is nothing but x of n into Ts minus x cap of n into Ts, because there is one more adder which subtracts, x cap of n into Ts from x of n into Ts, which results in E of n into Ts. Now we can say U of n into Ts is nothing but x cap of n into Ts plus E of n into Ts. Now this signal, this summation is nothing but x of n into Ts, and so the next sample is, the next term is quantization noise, right? Q of n into Ts, or quantization error, right? So ultimately what U of n into Ts is, U of n into Ts is nothing but x of n into Ts plus quantization error, right? So x of n into Ts plus quantization error. So the input is this prediction filter is x of n into Ts plus quantization error, right? So this quantization error will be very, very small. If the prediction is very good, prediction filter is very good, this E of n into Ts is very, very small. If the prediction filter, whatever it may be, if it is good or not, right, still it will have E of n into Ts, which is the difference between x of n into Ts minus x cap of n into Ts, which will be a nominal value. And usually prediction filter will be very, very giving up approximately close value to x of n into Ts. Okay, so the prediction, meaning what, after several samples we come to know, right? So what will be the next sample value? So any system can make, the prediction filter can make out or predict the future value of the next sample, right? So U of n into Ts is nothing but the input to the prediction filter is U of n into Ts, which is equal to x of n into Ts plus Q of n into Ts. Okay, so next we have even discussed this, the signal to noise ratio at the output of the demodulator, that is signal to noise ratio at the output, we can say sigma x square divided by sigma q square, where sigma x square is nothing but the variance of the input signal, and sigma q square is variance of the quantization error, right? Variance of the quantization error. Now the quantization error is the error, right? So we are aware of this quantization error, right? So delta, right, usually. So variance of the quantization error, sigma q square. And what we can do here, we can split this ratio into two parts, that is sigma x square, which is the variance of the signal, divided by sigma e square. Now this sigma e square is nothing but variance of prediction error, right? Variance of prediction error. Now if the predictor is very good, the variance of this prediction error will be very small, very small, and will be very small compared to the variance of the signal itself. Now this ratio will be GP, and this ratio will be very high if the prediction error is very small. The variance of the prediction error is very small. Sigma x square is much greater than sigma e square, resulting in this ratio GP is very high. We can consider this as a gain, which is a prediction gain. Okay, prediction gain. So prediction gain will be very high when this prediction error will be very small. And the next term here is sigma e square divided by sigma q square. Now this ratio SNRP, sigma e square, is nothing but prediction error, mean the variance of the prediction error, and variance mean ratio of variance of the prediction error to the variance of the quantization error, SNRP. We can say this SNRP as prediction error to quantization noise ratio, where GP is prediction gain. Okay, any doubts here? So the name differential pulse code modulation is the difference between the sample and its predicted value is what is resulting in differential pulse code modulation, right? We'll move on to the next kind of modulation scheme, that is conversion of analog to digital form. All right, before that we'll see the receiver. I think we have not discussed this receiver. All right, so DPCM, the incoming data sequence, you can see from the transmitter, it will be a binary data, maybe in the form of unipolar or polar form, right? DPCM data in binary form will be passed to the decoder, right? Decoder will result in the error value. At the output of the decoder we get error samples, and prediction filter is same kind of filter what we have used at the transmitter, right? Previous sample whichever has come, previous prediction error whichever has come has been given a proper predicted value, and to this next sample which has come will be added with, and resulting it in a particular sample, and this sample will be passed through a low pass filter to reconstruct the message signal. Okay, to reconstruct the message signal. This is what is DPCM receiver. Now, as far as prediction filter at the receiver is concerned, it is same, having the same property of the filter, that is prediction filter, which is used at the transmitter. Okay. Yeah. Any doubts? Any doubts? Next, we move on to delta modulation. Right. So, what this delta modulation is? Delta means very small usually, right? So delta modulation, it is special case of differential pulse code modulation scheme. Like DPCM, delta modulation is also a predictive waveform coding technique, right? So it is somewhat like DPCM, right? So it's a special case of DPCM, and it uses a quantizer of only 2 levels. Okay, there are only 2 levels for this quantizer, or we can say 1-bit quantizer, right? Only 2 levels means each level is encoded with 1 bit, right? So 2 level 1-bit quantizer, right? So you can see the step size of the quantizer, right? So step size of the quantizer, if the input, so you can see the quantizer, if the input takes on positive value, right? So input takes on positive value, the quantizer will quantize this positive value to delta, and if input takes negative value, quantizer quantizes it to minus delta. What is this input? What this X is? Let us see. But the step size of this quantizer, step size of this quantizer, you can say minus delta 2 plus delta. Step size, we can say capital delta, which is equal to 2 times delta. Okay. Now, as it is very only two level quantizer, it is very simple circuit compared to PCM or DPCM, right? The thing here is the main drawback of this delta modulation scheme is we need to, or the signal required to be sampled at the rate much higher than the Nyquist rate. That is the only thing, only concern in this delta modulation scheme. And there is a possibility of slope overload distortion in the waveform construction. We will see what this slope overload distortion when we come across the limitations of delta modulation. Okay, right? So you can see the step size delta equal to capital delta equal to 2 small delta. Okay, right? Now, how this quantization is going to be done? So it is somewhat like a differential pulse code modulation. What happens is signal is sampled at the rate much greater than Nyquist rate, and the signal sample and its approximation in the sense what prediction value will be considered, right? So if the difference between the signal sample and its predicted value is greater than 0, if the difference between the sample value and its predicted value is greater than 0, right? It's greater than 0, the quantizer quantizes it to plus delta. That means what? Step size will be increased by delta, right? If the difference between the sample and its predicted value is less than 0, the step size will be decreased by delta. That means minus delta. Step size will be decreased by delta. Okay, so you can say, take the signal. Let us say this is actually the signal x of t. Okay, and the square wave, you can see the raising or staircase kind of wave, what you can see can be considered as its approximation, right? Say for example, at this point of sampling interval, okay, the signal has a value something like this, and its predicted value is somewhere here. Okay, its predicted value is somewhere here, and the signal is somewhere here, right? Now, if at the output of the adder, right, the difference is positive, this minus this sample value minus this predicted value is greater than 0, then the step size will be incremented by delta. Okay, and the next sample somewhere around here it comes, right? Somewhere around here it comes, the next sample of the signal, and its predicted value, you can see it is greater than this sample value. What happens? The difference becomes negative, right? If the difference becomes negative, the step size get decreased by delta. So you can say the step size comes down by delta. Okay, so the next sampling interval somewhere here, if the next sampling interval is somewhere here, right, of the signal, and if x takes this sample value and the predicted output is this, predicted value is this, and you can see the difference, this difference is greater than 0. What happens? This difference is greater than 0. What happens? It will be incrementing the delta, right? So incrementing by delta, like this. You can see if the difference between the actual sample and its predicted value, based on the difference between actual sample and its predicted value, this approximation varies, right? You can get a staircase approximation. Suppose I'll take the signal as an example. Say for example, here I have this signal, okay, and say my approximation is somewhere here. This is the sampling interval. Now at this sampling interval, I find the signal difference is positive. This is actually the signal x of t, and say this is the approximation u of t, right? And at the adder, signal and its approximation, you can see the difference is positive. The step size will be increased by delta, let us say. Step size will be increased by delta, right? Somewhere here. Now, at this point of time, there is one more sampling interval here. You can see the signal value at this sampling interval is less than the approximation. What is going to happen? There is a difference which is negative. The sampler or the quantizer will decrease the step size by delta, right? So again, at this sampling interval, say at this sampling interval, the signal value is much greater than this approximated value or approximation, right? What happens then? The signal will be increased by approximation will be increased by delta, right? Again, it will be there for some time, and here at this point, the signal value is greater than the sample value, right? Signal value is approximation value, and here you find there is a rise in delta. The step size rather increased by delta, we can say, and it is going to be there for some time. And if the next sampling interval is this, the difference between the two sample is, right? So here, right, for the next sample it is like this, and you can say the difference something like this. Sorry. Here the difference something like this, it will be increased by delta and so on, right? So you can see how the coding is done, right? If there is a rising pulse, right, or rising staircase is rising or approximation is rising, the corresponding code will be 1. If there is a fall, right, here it will be coded as 0. So now I can say this part can be coded as 0. It is not considered here in the binary sequence. Then here this is 1 0. Then we have code for this is 1 1 1 1, right? And then here it is 0 1. Here it is decreasing, it's falling, right? So here it is 1, here it is falling, right? So 0 0 0 0 0 0 0, and here it is again 0 0, and it is rising here 1 1 1 1 1 0 1 0 0, and so on, right? So you can see if there is a continuous rise in the signal, corresponding code binary sequence is the same, right? Here 1 1 1 1 and so on. If there is a continuous fall like this, right, because it is an indication of a slope, increasing slope here, it is decreasing here, slope here. So if there is a continuous fall in the signal, you can see the code corresponding to the fall in the signal or signal sample is 0. Or in general, I can say if there is a slope in the signal, corresponding bits are going to remain same, right? 1 1 1 and so on, or 0 0 0 0 and so on, as long as there is a fall. And if you find a signal stable for some time, right, if the signal is getting settled for some time, stable for some time, you can see there is a alternate ones and zeros here. Are you able to follow it? Any doubts? Are you there?
Yes, sir.
Yeah. Any doubts
Yes,
you have? Yuvraj, any doubts you have?
No, sir.
Okay. right? Let us see the transmitter and receiver of the delta modulation, right? So this transmitter and receiver of delta modulation scheme almost same as the differential pulse code modulation schemes, transmitter and receiver. Now you can see in the DPCM we had a prediction filter, whereas in this we will have a delay. Okay, we will have a delay, and uh, the signal what x of n into ts is, its approximation is x cap of n into ts, x cap of n into ts. What is going to be done here is the difference between the signal sample and its approximation, or you can say delayed by ts, a past value will be taken, and resulting signal will be e of n into ts. Now if this e of n into ts is positive, the step size will be increased by delta. If e of n into ts is negative, the step size will be decreased by delta. Now what you can see here is, have a closer look at this part, right? This part, it is nothing but an accumulator, right? Accumulator x of n into ts is nothing but a u of n into ts, and u of n into ts is nothing but u of n into ts minus ts is nothing but u of n into ts, uh, which is delayed by, I mean not ts, u of n into ts is nothing but delayed by ts. Ts is nothing but the sampling interval, right? So the signal will be sampled at the rate of fs, and where fs is nothing but 1 by ts. Okay, right? And u of n into ts, hello, who is this? Aditi.
సరే బయలుదేరి
Pranay.
ఆ,
Pranay,
ఆ,
please mute yourself.
నేను
Yeah. Yeah, any doubts? Right. So let us see the analysis here for this delta modulation scheme, right? So E of n into Ts, you are able to see the slides, no? Are you able to see slides?
Yes, sir.
Okay. E of n into Ts is nothing but x of n into Ts minus x cap of n into Ts, where x cap of n into Ts is nothing but u of n into Ts minus Ts. And b of n into ts, what b of n into ts is, right? B of n into ts we have seen, right? We have seen the uh, we have seen the characteristics, sorry, we have seen the characteristic of the quantizer, right? Right, minus delta plus delta for the input x, right? Characteristic of the quantizer is this, right? Now b of n into ts is nothing but the encoded data, right? So b of n into ts, whether it is in right, we have not taken it as a binary which form, it is a, by default nrz polar form, right? So what b of n into ts is, depending on the type, I mean depending on the value of e of n into ts. If e of n into ts is positive, it is scaled by delta. If e of n into ts is negative, it is scaled by minus delta, plus delta or minus delta. That means what? If it is positive, e of n into ts is positive, b of n into ts is as good as logic 1, right? B of n into ts is as good as logic 1 if E of n into ts is greater than 0, it is 1. Else if else if it is 0, E of n into ts is less than 0, it is negative. It is 0 if E of n into ts, sorry, minus delta, right? It's binary. Logic 0, it is 0, right? Logic 0 I am talking, logic 0, logic 1 here. If E of n into ts is less than 0, and correspondingly voltage level is plus delta here, here it is minus delta. Okay, plus delta if E of n into ts is greater than 0 and it is as good as logic 1 and its amplitude is delta. And if E of n into ts is less than 0, it is logic 0, it is as good as minus delta. So you can see this binary signal is in polar form. Okay, in polar form. Binary signal is in polar NRZ formats, right? B of n into ts is nothing but delta times signum of E of n into ts. Why signum? It's a characteristic of the quantizer. Now let us see what is this U of n into ts. U of n into ts is nothing but past value of U of n into ts plus B of n into ts. B of n into ts is nothing but the scaled by signum function, right? So you can see this U of n into ts minus ts is nothing but the past value of U of n into ts. It's a past value of U of n into ts. What you can say that now, that is, this can be written as summation I equal to 1 to n past values U of n into ts, past values, right? B u n represents here present value, and this remaining past values from 1 to n minus 1 is this, right? Delta summation I equal to 1 to n signum of E of I into ts, I into ts, right? So resulting U of n into ts is summation I equal to 1 to n bi of ts. What it indicates, it is summation, it is summing up past values, past bits or past deltas. Okay, it is summing up past deltas, right? U of n into ts is nothing but the sum of past as well as present delta, that is I equal to 1 to n past deltas as well as present delta. Deltas depending on, right, the error, right? It can be plus delta or minus delta, right? So it is nothing but summation I equal to 1 to n past sum of past deltas, right? Past deltas. Or you can say this U of n into ts is nothing but an accumulator. This whole part is an accumulator. What this accumulates? It accumulates the past sample values, past bits. It's going to accumulate. Okay, right? Similarly, similar to the DPCM receiver, we have a delta modulation receiver. So incoming binary data, right? The past value which is already come gets added and passed through the low pass filter, right? It's passed through the low pass filter to reconstruct the message. Okay, so this is about delta modulator, right? So difference between the delta modulator and DPCM is the difference is x of n into ts is nothing but accumulated value, right? Accumulated value, right, of the accumulated value of the samples in the past, right? X of n into ts minus its prediction or its approximation we get. Okay, fine. Any doubts here? Any doubts, Yuvraj? Are you there or?
Yes, I'm here, sir.
Okay. Any doubts?
No, sir.
Revant Garg. Revant, are you there?
Yes, sir. Yes, sir.
Murli Krishna. Murli Krishna. Mungamuri, Murli Krishna. Are you there? No. Prathamesh.
Yes, sir. Yeah, I'm hearing, sir. No doubt, sir. You could go ahead, sir.
Now, the limiting factors in delta modulation scheme, there are two uh, sources which can affect the performance of the delta modulation scheme, right? There are two errors we can say. One is a slope overload distortion, the other one is granular noise. Both are dependent. Okay, slope overload distortion and granular noise, right? So there is a possibility of continuous slope in the signal, and if that is the case, what will happen with the delta modulation scheme? And if that is the case, if a signal is right stable for some time, there will be a granular noise. What will happen with the performance of the delta modulation scheme? Let us see. Let us take a signal as an example, right? This x of t is the signal, let us say. Okay, x of t is this signal, right? For some time there is a continuous rise in the signal, or you can say steep, I mean continuous sharp rise in the signal. Okay, and for some time the signal is stable. Okay, now if we take the delta modulator scheme for this, let us say we have signal is sampled at the rate much greater than the Nyquist rate, and this is the sampling interval. So a sampling interval we have ts, right? This is the first sample I have, and say this is the next sample I have, right? So here at this point of time the next sample is, but by the time the next sample arises, its level, its value will be such a high that its approximation will not be able to reach to that. You can see its approximation will not be able to reach that now at this sampling interval, right? And the approximation right here, you can see it will be reached to this level, and it is going to remain stable for the next sample to come, right? Say next sample has come somewhere here at this point of time, and the difference between these two approximation is much greater than 0, but the delta modulator can make it rise up to delta only, height of delta, right? So the next sampling interval you can see somewhere here, right? But the sample value is much greater than the past value, resulting in this approximation whose value is much less than this sample value. It will get an height, it will get a jump of delta, but it will be still less than that. It is going to remain stable here, and for some next sample value we get somewhere here, and you can see this approximation, right? This is approximation for x of t, that is u of t, right? So this x of t get an approximation u of t. What has happened with this approximation is, this approximation has deviated a lot from the actual signal. Okay, has deviated a lot from the actual signal is this, right? With the continuous slope, very sharp slope, like this, right? You can see the approximation is deviating away from this actual signal. Okay, and this deviation leads to the slope overload distortion, right? At the receiver it will be very difficult to reconstruct, because there is a huge difference between the actual signal and its approximation. It looks, right, it looks as if there is a huge difference, right? This may cause the problem with the performance of delta modulator. Okay, now with this step size, and if we find the same signal is stable for some time, right, stable for some time, there is a rise in the approximation, and again there is a fall here depending on the difference between the signal or sample and the approximation. There is a rise, fall, and rise. You can see there is a rise, fall, a signal level or approximation level much lower than the signal sample level, right? So this noise, or this results in loss of signal, right? So this loss of signal is nothing but granular noise. Okay, so if we have the signal with a slope like this, we face or the delta modulation suffers from slope overload distortion. And if the signal has some stability for some time, there will be granular noise. How to overcome this? How to overcome this? Can anyone tell me? Yuvraj?
Sir, delay.
Yeah?
Sir, we need to increase the sampling rate. Or
I have increased the sampling rate to greater extent, right? I have increased the sampling rate. What should I
So
do?
we reduce the time of TS probably.
Yeah, that's what sampling rate increasing means, reducing the time of T of S. But still I find this. What I can do?
So increasing the levels.
Increasing the height, I mean the step size. What I'll do, I'll just increase the step size here. When I find this, there is a slope, right? Isn't it? I increase the step size so that I can go very closer to the actual signal, right? If I increase the step size here, what will happen here? If I increase the step size here, I will be able to overcome with the slope overload distortion, isn't it? Here, are you able to make out the pointer, Ayush?
Yes, sir.
If I increase the step size here, I can easily come out with, right? I can easily remove the slope overload distortion if I increase the step size here. But if I continue with the same step size here, what will happen?
So the
Granular.
noise will increase.
Granular noise will increase, right? So my system should be in such a way that if there is a steep slope, my approximation or the quantizer should be, or the step size should be increased in such a way that if there is a steep slope, it should increase the step size continuously. If there is a settling time for the signal, right, signal doesn't change, right, then we have to decrease the step size, right? So we have to find a way to do it. So who can tell us? One system which can tell us to do that is adaptive delta modulation scheme, right? Adaptive in the sense what? Based on the approximation, right? Based on the slope, it will increase or decrease the step size of delta, right? If the step size is, I mean, if there is a slope, continuous slope like this, increase the step size. If the signal is getting settled, then decrease the step size. Who can do that, right? To eliminate the slope overload, before that, what we need is slope overload distortion. To eliminate, we need this ratio. Delta is the step size divided by TS. TS is sampling interval must be greater than or equal to maximum slope of the signal, okay, which must be greater than or equal to maximum slope of the signal, right? So this is what is required. So you need to have delta by Ts, right, much greater than maximum of dx by dt. Now in the denominator, you said, some of you have said we have to reduce Ts. Of course, even if we reduce Ts, right, if we don't increase delta of S in cases of signals with steep slope, I mean very sharp slopes, it is required that with the Ts reduced, delta also to be increased, okay, right? And as far as granular noise is concerned, what we have to do, we have to decrease the step size. Who can tell us, right? So the signal can vary, right, at different times, right? At different times signal can vary. There can be a steep slope, there can be a no slope, there can be a stable signal, right? So we need to have a system which can adapt to the signal, and based on the nature of the signal, we increase or decrease the step size, right? So to do that, we have one system called adaptive delta modulation system, right? So it is just a delta modulation system, but additionally we have a step size controller, right? Step size controller. Step size can be made to decrease, I mean, move to, right, delta min less than or equal to delta of n into Ts, right? Right? Delta max. So this step size controller varies this delta minimum to maximum. When it should be minimum? When this delta minimum should be, I mean, well, delta of any TS should be minimum. There is when there is a signal which is settled, right? When this has to be maximum delta of any TS, when there is a steep slope, you increase delta. Now, delta of any TS is made to vary, by a circuit called step size controller. Is a step size controller, right? So what we have to do? Delta min is made to vary I mean, delta n into ts is made to vary between delta min and delta max. Okay, right? The adaptation rule, right? Adaptation rule for delta of n into ts is delta of n into ts is equal to g of n into ts into delta of n into ts minus ts. Now, based on the past value of delta of n into ts, you have to vary the delta of n into ts, right? How to vary? How to get this? How to get this g of n into ts? G of n into ts will be scaled. I mean, this delta of n into ts minus ts will be scaled by k if b of n into ts is b of n into ts minus ts. What is this? What this indicates? B of n into ts equal to b of n into ts minus ts. Can anybody tell me, Yuvraj?
Sir, it means that if the current output is the same as the previous output, no scaling is required.
Encoded output. Okay. Yeah, if I have one, I mean, past value, and if past value is 1, present value is 1, right? So past value is 1, present value is 1. What it indicates? If I go back, if the past value is 1, here past value is 1, present value is 1, past value is 1. You can see the past value is taking the same value, and in this case, when there is a slope, the values are the same, encoded values are the same, and when there is a slope here, encoded values are same, that is zeros, continuous zeros you have. What it indicates?
Steep slope.
Steep slope. It indicates steep slope. Right? If the present value is same as past value, you have to scale the past step size so that it increases. Okay, so it increases the past step size. K is the factor which increases the step size. And if the present value is not equal to past value, you can see the same diagram again. If the present value is 1 and past value is 0, what it indicates? Right? If I get sequence like this 1 0 1 0 1 0, right? What it indicates?
A set is
Yeah.
a set
Slope is very close to zero.
Yeah, signal is getting, I mean, it's almost not varying, right? It's almost constant, is not varying, signal is not varying. In that case, what you have to do? You have to decrease the step size, right? The standard step size value is k equal to 1.5. This standard factor, right? Sorry, not the step size value. It's a factor k is 1.5. That's a practical value used in the adaptive delta modulation. Only the thing is, the adaptive delta modulation is same as delta modulation, but the step size control, right? Step size control based on the past value, right? And the present value, this step size is controlled. Okay. Any doubts here? Any doubts? Any doubts? Any doubts? Murali Krishna, Yuvraj,
No
any
doubt,
doubts?
sir.
Yeah, please.
No doubt.
Are you able to understand?
Yes, sir.
Nagam Pranay, Revant Garg, are you there?
Yes, sir, I'm there. No doubt, sir.
Pranay Bharat Reddy, Pranay, Ashwin Krishna, you are simply there
Yes, sir.
or not?
Yes, sir. I'm there.
Yeah. Okay. So with this, we have completed the waveform coding techniques. Okay. As far as baseband modulation schemes are concerned, I have completed my topics on baseband modulation scheme. The next scheme, I'll be moving on to is uh, passband modulation scheme. To begin with, I'll do the QPS scheme. Now, what I'll do is I will stop the recording as far as this baseband modulation scheme is concerned. I will restart the recording for QPSK when I begin with QPSK. And also, you can go through my folder in the files, right? I have uploaded one file with problems with solution to that. You just go through. Okay, if you face any difficulty, you just let me know. Okay, you can just send a message to me in the group, or you can send a WhatsApp message to me, right? Okay, if you face any difficulty in understanding the concepts of the topic that I have covered, you can discuss with me. Okay, fine. I'll just stop the recording for now, and next when I begin with the passband modulation scheme, I will start the recording. Any doubts?
No, sir.
So
Ah,
so realistically, when we use
your
this
voice is not
data
audible.
modulation,
One second, one second.
sir, am I audible now?
Well, wait. Yeah.
So realistically, when we use delta modulation or this adaptive delta modulation, how much faster do we have to sample the data compared to say the Nyquist rate?
See now, suppose I have a 1 kilohertz signal. Okay, message signal I have a 1 kilohertz, right? I need to sample it at the rate much greater than Nyquist. What is the Nyquist rate?
So
2
2
kilohertz.
kilohertz.
Yeah.
Yes.
Right. If you are having sufficient bandwidth, you can afford to sufficient bandwidth, you can even go for 20 kilohertz sampling rate, 20 kilohertz, 30 kilohertz, like that. Okay, right.
Okay,
And
sir.
if the yeah, it is you who will have to decide based on your limitations, your budget. Okay, if you have sufficient bandwidth, sufficient cost, right, so then you can go for the sampling rate that you want. Yeah.
Okay, sir. Thank you.
Okay. Yeah. Any doubts? As far as bandwidth requirement is concerned, how good this DEM or DPCM is with respect to PCM? Can you tell me, Yuvraj?
It uses a lot more bandwidth because you're
Yeah.
sampling at a much higher rate.
Yes. Because in DEM you need only 1 bit per sample, right? 1 bit per sample, right? Sample is each and every sample is assigned with only 1 bit. That is the reason why you need very less bandwidth compared to PCM and even DPCM. Okay, right. Now I will move
Excuse
on
me,
to
sir.
yeah.
In delta modulation, agreed
Yeah.
that the quantizer only uses 1 bit at a time, but you also have to sample at 10 times the rate, like you said
Yes,
in
yes,
just the example you
that is,
gave.
that is what is required. That is what is required. But if I have say 1024 levels in right PCM, right, how many bits I need per sample? 10 bits per sample, right?
Yes,
And
sir.
the bandwidth I require, say if I sample the signal at the rate fs equal to 1 by ts must be equal to n times 10 times tb, right? Bit duration is tb, right? So
Hmm.
that's what is required, right? That is ts, and the bandwidth is 1 by ts, what it is. Okay, fine. Okay. uh, Next I will move on to I will start recording again, and this recording is for passband modulation scheme. Okay. Quadrature modulation techniques is one of the passband modulation scheme. The two coherent quadrature modulation scheme. What do you mean by coherent quadrature or coherent modulation technique? You have discussed, you have studied BPSK, you have studied FSK, right? You must have studied ASK, right? These are all the modulation techniques you studied as coherent modulation techniques. And even in analog communication, you have studied some of the modulation techniques, or most of the modulation techniques are coherent modulation techniques. What do you mean by coherent modulation?
Sir,
Yeah.
Coherent modulation basically means that at the receiver there is a source of the carrier signal which is in phase with the signal generated, carrier generated at the transmitter.
You need to have a carrier reference at the receiver to demodulate. So it is resulting in a coherent modulation scheme, right? You have studied in analog communication, right? You have studied double sideband suppressed carrier. You have studied SSB, the single sideband suppressed carrier. You have come across VSB also. In that you have both. You have studied both. Coherent as well as non-coherent modulation or demodulation. Okay, based on the demodulation technique, we decide the kind of modulation is a coherent or non-coherent. Okay, so what is non-coherent then? What is non-coherent modulation? Praveen?
So when you
Yeah,
when
Kunal.
we won't need the same carrier source
We do
in
not use
phase
carrier as a reference, or we do not take carrier reference, or local oscillator will not be used at the receiver to, right, to demodulate. So we go for, we say it is non-coherent. Okay. Okay. So now we have seen baseband modulation and passband modulation. What is the difference between the baseband modulation and the passband modulation? Baseband modulation is nothing but the way of converting an analog signal to digital form. It is baseband. It is going to be still an information. Okay, baseband in the sense signal has a spectrum which is centered around frequency f equal to 0. When we discussed a pass band modulation scheme, a signal whose spectrum is centered around a frequency called fc, which is nothing but the carrier frequency. Okay, it is pass band modulation. So you have studied BPSK, you have studied ASK, you have studied FSK as well, right? Now we will study quadrature modulation technique. What do you mean by quadrature modulation technique? In that we have studied, I think, quadrature carrier multiplexing. What do you mean by quadrature carrier multiplexing? So what is quadrature carrier multiplexing? You have seen this equation in the past, right? When you studied analog communication part, right? So you have seen S of t equal to mi of t or m1 of t cos 2 pi fct plus or minus m2 of t or mq of t sin 2 pi fct. What it indicates, mi of t and mq of t. Now if I treat these mi of t and mq of t as two different signals, okay, and these, we say these two signals, these two different signals on a single carrier, okay, these two different signals on a single carrier, these two m1 of t or mi of t and mq of t are on a single carrier. So one is in phase with the carrier and the other one is it with in quadrature with the carrier. So cos 2 pi of fc of t is orthogonal or perpendicular, I can say, is sin 2 pi fc of t, right? So you can say this mi of t as in phase component and mq of t as a quadrature component. So because it is scaled by quadrature carrier, okay, cos 2 pi of c of t is a carrier, Sine 2 pi fc of t is also a same carrier, because it is in phase quadrature with, right? So it is in the phase pi by 2 with cos 2 pi fc t. Okay, right? So if these two messages, right, mi of t and mq of t are two different data, binary data. This is one binary data, this is another binary data. Can we place these two binary data on the same carrier, right? One is in phase with the carrier and another with quadrature, right? So we can place the same data, right? Instead of the signal, now we are going to place binary data in the carrier. So that is what is going to result in quadrature modulation, right? So you can see both mi of t and mq of t can be related to the input data, binary data. Okay, so now this leads to a quadriphase shift keying, right? QPSK, sorry, QPSK, it is QPSK, please, P is not the QPSK, okay, right? It is quadriphase. I'll just change it. SK, right? Quadriphase shift keying. So what this quadriphase shift keying is, right? This is a bandwidth conserving modulation scheme, right? So our design goal is usually to have minimum probability of error, maximum power transmission, minimum using minimum bandwidth, right? Right. So many things is our goal, but all goals cannot be reached in one modulation technique. And one of the goals that we can achieve, that is bandwidth conservation, minimum bandwidth utilization we can do is bandwidth, this modulation technique, that is quadriphase shift keying. It's a bandwidth conserving modulation scheme, because 2 bits, right, 2 bits at a time are going to be placed on a carrier, right? So in fact, when I say phase shift keying, quadriphase shift keying, you have studied BPSK, right? What the meaning of BPSK is? What is the meaning of BPSK? Yuvraj, what is BPSK? Binary phase shift keying?
Yes, sir. There we change from 0 to 180 degrees phase shift depending on 0 or 1.
Information is present in the face of the carrier, right?
Yes, sir.
Yeah, information is present in the face of the carrier. And here also we will see that information is present in the face of the carrier, right? 2 bits at a time are present in the face of the carrier, right? QPSK, quadriphase shift keying, right? So information carried by the transmitted wave is contained in the face. Now information we are going to place in the face of the carrier, okay, right? So face of the carrier can take, how we can place this information in the carrier, right? We can place in the face values spaced, equally spaced, such that pi by 4 we have one combination, 3 pi by 4 another combination, 5 pi by 4 third, and 7 pi by 4 is the another phase. So we are going to place these in quadriphase, right? 2 bits at a time. 2 bits at a time in the sense what? It can be 0 0 0 1 1 0 1 1, right? So we can place them in the phase pi by 4, 3 by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. Okay, right? And we can express the modulated wave SI of t. SI of t is, right, square root of 2e by t. This root even takes the t inside, okay, right? Square root of 2e by t cos 2 pi fct plus 2i minus 1 pi by 4, right? Where I can take value 1 2 3 4. Now if I equal to 1, right, one set of binary data will be present in pi by 4. If I equal to 2, right, one set of binary data will be placed, taken care by 3 pi by 4. If I is equal to 3, right, one set of, right, data will be placed or taken care by 5 pi by 4, and so on up to 7 pi by 4, right? So, and E is the transmitted and it is 0 otherwise. As usual, we have seen for binary phase shifting, the symbol width is T, right? Symbol width, symbol I say now, not the bit, right? Two bits together, one symbol, T is symbol width. E is the transmitted signal energy per symbol, right? Right? This is the energy per symbol, not per bit, energy per symbol, right? So what are the symbols, right? So T is the duration of the symbol, right? And frequency, FC, right? Carrier frequency is nothing but integer multiple of 1 by T, right? Integer multiple of 1 by T for some fixed integer NC, right? So NC by T we can say, right? Right? Each phase value corresponds to a unique pair of bits, right? Each phase value, right, is going to correspond to a unique pair of bits called a dbit. Dbit means what? Two bits together. It can be 0 0, it can be 0 1, 1 0, or 1 1, right? Two bits together, a dbit. Okay, two bits together, a dbit. Right. So let us, we may choose a gray scaled or gray encoded set of dbits 1 0, 0 0, 0 1, and 1 1. Okay, 1 0, 0 0, 0 1, and 1 1. Let me tell you one thing here. If one symbol, binary symbol, if it is 1, we can consider it is in enlarged polar form with some positive value, and if it is 0, we can say it is again in enlarged polar form with some negative value. This 1 is positive value, 0 is negative value. Again 0 0 both indicates both are negative. 0 1, 1 is negative, 1 is positive, and 1 1 both are positive, right? Right. So like that we can have the expression for the modulated wave SI of t. We have seen in the past, that is SI of t is nothing but square root of 2e by t cos 2 pi fct plus 2i minus 1 into pi by 4, right? Now if I say expand cos a plus b, I'll get cos a cos b minus sin a sin b, right? Right. So here it is cos 2 pi.
Sir,
Yeah.
sir, how did we get the expression in the last slide? The root 2e by t 1.
Root 2 e by t.
Sir, how did we get this SI of t expression?
Yeah. Now, our intention is to represent a signal as a linear combination of n orthonormal or orthonormal basis functions, right? That is the first thing. Okay. Got it? That is the first thing we need to see. We can represent any signal as a linear combination of n orthonormal basis function. And now the existence of this signal is between 0 to t. Duration of this signal is t, capital T, right? Now to represent this SI of t as a linear combination of n orthonormal basis functions, we need to have this basis function to have unit energy. Okay, got it? Unit energy. That is the only reason, right? That is the only reason. How in the BPS case scheme, square root of 2EB by TB, how you got? Can you tell me? Square root of 2EB by t sub b cos 2 pi fct plus pi. How you got? You did not try to find out in BPSK how many basis functions you have? Hello, who raised it? Are you there?
Yes, sir.
You are there, no? Yeah, tell me in BPSK how many basis function you have? How many basis functions you have?
Sir, 1.
One basis function, right? How you could define a 2EB by t sub b, right? The basis function there was square root of 2 by tb cos 2 pi fct, right?
Yes, sir.
2 by square root of 2 by tb cos 2 pi fct. Why you have chosen? Total energy in that signal is? Hello. What is the total energy in that signal? Duration of that signal was 0 to t sub, t sub b, right? So energy of the signal was one unit. That is the reason why here we want to have the basis functions with unit energy. That is the only reason for taking 2e by t, square root of 2e by t, where e is the energy of the signal, binary signal, binary, so rather symbol, and t is the duration of the symbol. Okay, and the signal existing for a duration of capital T, that is 0 to t, and rest other places it is going to be 0. Okay, right? So here, so I missed out, I think, cos 2 pi fct, right? If I expand cos, if I expand cos a plus b, I'll get cos a cos b minus sin a sin b. Right? It's just an expansion of equation 1 what we had, right? Right, so square root of 2e by t cos 2i minus 1 pi by 4 minus square root of 2e by t sin 2i minus 1 pi by 4 into sin 2 pi fct, right? Now, where I equal to 1, 2, 3, 4, right? So what are the observations here? There are two basis functions, right? One is cos 2 pi fct, another one is sin 2 pi fct. So we are choosing pi 1 of t is equal to square root of 2 by t cos 2 pi fct, phi 2 of t equal to square root of 2 by t sin 2 pi fct. Why? What is the reason behind choosing this? Can you tell me? The person who has raised doubts, can you tell me why pi 1 of t equal to square root of 2 by t cos 2 pi fct and phi 2 of t equal to square root of 2 by t sin 2 pi fct, right? There are two basis functions now. Why? Hello?
Yes, sir.
Yeah, tell me. Now you should be in a position to tell me. If you have understood the doubt that you had, I cleared. Yeah. What is the reason for phi 1 of t to be square root of 2 by t cos 2 pi fct, phi 2 of t to be square root of 2 by t sin 2 pi fct? Yeah. Getting or not? You are getting or forgetting? Hello? Yeah. Tell me. Can you tell me, Ayush? Ayush? Are you there? Are you there, Ayush? Yuvraj?
Yes, sir.
Yeah.
Um, what exactly are we asking? Why did we get these two basis
Yes,
functions?
yes, yes.
We got these two basis functions because in the expansion of SI of t, we have a constant for any given symbol. We have a constant in front of this cos 2 pi fct and a constant in front of sin 2 pi fct. So we can now express it in vector form. So the basis function is phi 1 and phi 2, which is what we got.
What is the reason behind taking square root of 2 by t cos 2 pi fct or 2
Uh,
by t sin 2 pi fct or 0 to t?
because Yes, I was saying that we need to take that root of 2 by t because to get the unit energy of the basis.
The basis function has to have unit. That is the only purpose, to have unit energy of the basis functions. Okay. So now I equal to 1, 2, 3, 4. The observation what we have is two basis functions. Right? We have now two basis functions. That means what? Si of t can be expressed as a linear combination of two orthonormal basis functions. Si of t, whether it is S1 of t, S2 of t, S3 of t, S4 of t. We can express as linear combination of two orthonormal basis functions. Okay, phi 1 of t, phi 2 of t, right? So we get 4 message points then, right? We get 4 message points. That is, vector Si can be expressed as square root of e cos 2i minus 1 pi by 4 and minus square root of e sine 2i minus 1 pi by 4, right? So I can write this Si of t is equal to Si of t is equal to, that is, root of e cos 2i minus 1 pi by 4 phi 1 of t plus, plus, not plus, minus square root of e sine 2i minus 1, right? Sine 2i minus 1 pi by 4 phi 2 of t, right? So linear combination of two orthonormal basis functions, right? S1 of t, S2 of t, S3 of t. Now these points, right? These are the scalars result in a vector correspondingly, right? So Si, vector Si can be written as square root of e cos 2i minus 1 pi by 4 minus square root of, right, e sine 2i minus 1 pi by 4. It can be written even as si1 si2, right? So you just try to recall Gram-Schmidt's orthogonalization, right? si1 si2 now, right? si1 si2, right? So now we can have these points, right? We can have these points in the uh, two-dimensional vector space, that is Si, vector x Si here can be Si1, Si2. This is corresponding to a vector S1, S2, S3, S4. Okay, S1, S2, S3, S4, right? You can see here corresponding points, right? So Si1 and Si2, S1, square root of whole square root. Now you can see for I equal to 1, square root of e cos 2i minus 1 pi by 4. For I equal to 1, that is cos pi by 4 is how much? Cos pi by 4 is 1 by root 2, right? Square root of e by 2, right? Right? Square root of e by 2 and square minus square root of e by 2, and 3 by 4, 3 pi by 4 s2, vector s2, I can say minus square root of e by 2 minus square root of e by 2, and s3 minus square root of e by 2 and plus square root of e by 2. S4, the face contains, right, I mean value 1 1 and corresponding amplitudes, right? Square root of e by 2 plus e by 2, right? Square root of e by 2. Now one thing you can observe, if the first bit is 1, next bit is 0, correspondingly Si1, here it is positive, here it is negative, right? You can say 1 is having an amplitude, right, square root of e by 2, right? And here 0 is having an amplitude square root of e by minus e by 2. So right, so 1 and zeros are in polar format, NRZ polar format. Now suppose 0 0, both are negative. 0 1, for 0 it is negative here, positive here, and for 1 1, right, both are positive, right? So both scalars are positive. Correspondingly vector we have S4, right? So we can have these vectors as S1, vector S1 for 1 0, square root of e by 2 minus square root of e by 2, 0 0, both negative, 0 1, 1 negative, 1 positive, 1 1, both positive. Okay, these are the vectors. That means what, we can express these vectors in two-dimensional vector space. So vector space, two-dimensional means what? Represented by basis functions here, basis functions phi 1 and phi 2. Now what actually these basis functions represent here in modulated wave? Can you tell me, Yuvraj? Phi 1 and t, phi 2 of t are now basically basis functions, of course. They are
the carrier waves.
they represent carrier, right? So they represent carrier, right? So basis functions representing carrier here. Okay, so next we can have two-dimensional representation or constellation for quadriphase shift key signal. constellation for quarter phase shift keying. You can see based on the points, that is S1, S2, S3, S4, right? Right. So where you expect this S4 to come? 1, 1. Where this you expect in two-dimensional vector space?
First quadrant.
First quadrant. Here in the x-axis minus second quadrant. Here it is in the third. Here in the fourth quadrant. Right? So like this, we can draw the signal space diagram for QPSK, and we also call it as a signal constellation. Right? Signal constellation of QPSK. You can see message point corresponding to dbit 1, 1 is here. Right, which is in the first quadrant, right? Message point corresponding to 0, 1 in the second quadrant, message point corresponding to 0, 0 in the third quadrant, message point corresponding to 0, 1, 0 is in the fourth quadrant, right? So this is nothing but the signal space representation or vector what do you call constellation of QPSK. Okay, right. So now the signal space. Now you can see the QPSK transmitter, how it look like, right? So binary data sequence I have, and this binary data sequence converted it to polar form, right? Polar NRZ form, and this polar NRZ form is passed to a demultiplexer, right? So we can say first bit comes here, second bit comes here, third bit, fourth bit, fifth bit, sixth bit, or I can say odd bits or odd position bits come here, even position bits come here, and these bits have some amplitude, right? You can see it's square root of e by 2 if it is amplitude, right? It is getting multiplied by the basis function phi 1 of t equal to square root of 2 by t cos 2 pi fct, right? And resulting in 2e by square root of 2e by t cos 2 pi fct here, and this even numbered bits coming here, resulting in square root of e by t sine 2 pi fct. So this part is written as square root of e by t, 2e by t rather, 2e by t cos 2 pi fct, and here I can write 2e by t sine 2 pi fct, right? Sum of these two resulting in a QPSK signal, and it is getting transmitted. What you can see here, signal is carried on a single carrier. One is having in phase, one is in phase, other one is quadrature carriers, right? So cos 2 pi fct is orthogonal to sine 2 pi fct, and the role of basis function here in this case is nothing but carrier. Okay, carrier, right? Role of this is nothing but carrier, right? So now what we see here, signal space is partitioned into 4 regions, right? So we need to decode, right? We need to decode the signal at the receiver. If the signal point falls inside the region corresponding to 1, 1, or it falls inside the region Z4, we decide in favor of 1, 1. If the signal point at the receiver falls, or signal vector falls inside the region corresponding to 0, 1, we decide in favor of 0, or it falls in the region Z3, we decide in the favor of 0, 1. If the signal vector falls inside the region corresponding to Z2, we decide in favor of 0, 0, right? If the signal falls inside the region for Z1, we decide in favor of Z1. That means the decision at the receiver is based on the signal point, the observation point, how close it is with the actual signal point. How close mean the sense what? It has to fall inside the region of certain region, so that we can decide in favor of it, right? So we know, right? So we have already seen that two-dimensional space, if signal points are like this, we can partition this two-dimensional space into 4 regions: Z1, Z2, Z3, Z4, right? Now if we talk about the receiver, right? So transmitted signal is SI of t, right? SI of t. So along the transmission line, so signal get affected by noise, and Due to that, we get signal x of t, which is nothing but si of t plus w of t, right? We get the signal x of t, which is different from the transmitted signal in the presence of noise, right? What is the meaning of coherent detector? Coherent detection is nothing but we use the carriers as reference at the receiver, right? Signal is now passed through, incoming signal x of t is now passed through this bank of correlators, right? So you can say this, so far you have seen only one correlator, right? Example, only in the case of frequency right shift keying you have seen two correlators, but you have bank of two correlators now, right? So the x of t, this x of t is multiplied by phi 1 of t, is passed through a bank of passed through an integrator, and resulting sample value is x1, and here you have resulting sample value is x2. Now this x1 and x2 can be considered as a vector, right? Vector x1 and right x1 and x2, right? This one vector, right? X can be considered, considered here, right? Where x1 is scalar, x2 is also scalar. Now both are random variables. So these are random variables, right? X1 is a random sample value of a random variable capital X1, and x2 is a sample value of a random variable capital X2, I can say, right? So x1 and x2 are random, right? So now this vector, right? This vector, if it falls inside the region Z4, we decide in favor of 1 1. This vector x1 x2, if falls inside the region, right, for Z3, we decide in favor of 0 1. If it falls inside the region Z1, right, we say it is 1 0, right? What the decision device will do here, device will check if x1 is greater than 0, it will be decided in favor of 1. Okay, if this x1 is greater than 0, it will be decided in favor of a 1. If x1 is less than 0, it will be decided in favor of a 0. If x2 is greater than or equal to 0, right? Sorry, if x2 is greater than 0, it will be decided in favor of 1. If x2 is less than 0, it will be decided in favor of a 0. Here x1, if it is greater than 0, it will be decided in favor as a 1. x1, if it is less than 0, it will be decided as 0, right? So you can see here in the signals constellation, right, for us to decide the received vector in favor of 1 1, x1 must be greater than 0. So this x-axis corresponding to x1, y-axis corresponding to x2. For a signal, for a vector to be decided as 1 1, x1 must be greater than 0, right? For a vector to be decided as 1 1, x1 must be greater than 0 and x2 must be greater than 0. Then only we can say the observation vector is inside region Z1, Z4, and it belongs to symbol 1 1. Okay, any doubts here? Any doubts?
No, sir.
Yeah. Let us say S4 is a transmitted signal, right? S4 is a transmitted signal in the sense what it contains. It is containing the information about 1 1, right? So 1 1 is contained in the face of the carrier, right? S4, right? 1 1 is the one, right? So to find the probability of error, right? So our main analysis is the performance analysis, right? So whether it is a very good performing system or not. For that, what we do, we just evaluate the probability of error of that system, right? If we talk about the QPSK, we can evaluate it by probability of error, how minimum probability of error it can have, right? Probability of error it can have. So for that, what we do, we take a signal S4 of t to find bit error rate. Okay, our main intention is to find bit error rate, right? To find out the probability of error, let us find the probability of receiving correctly, right? Receiver making correct decision. Probability of error is receiver making wrong decision. Probability of no error is receiver making correct decision. I mention it as PC, right? PC as making a correct decision, right? PE is the probability of error, where PE is equal to 1 minus PC, right? At PC is the probability that received vector falls inside the region Z4, right? If at all I have transmitted 1, 1, it has to fall inside Z4. For that, what is required? X1 must be greater than 0, X2 must be greater than 0, right? Right? So then what is the probability of making correct decision, right? So X1, you can see this X1 and X2 are the sample values of random variables X1 and X2, and which are statistically independent, right? Capital X1 and X2 are statistically independent. There is a reason why. Probability of making correct decision is probability density function, that is 0 to infinity, integral 0 to infinity 1 by pi n square root of pi n naught e to the power minus x1 minus square root of e by 2 by n 2 whole square by n naught dx1. What this stands for? Square root of e by 2. This is the mean value of a random variable x1. Okay, mean value of a random variable x1. And what is this? This is actually mean value of a random variable x2. As both are statistically independent, probability of making correct decision is also independent, right? So you can see 0 to infinity 1 by square root of pi n naught e to the power minus x1 minus square root of e by 2 square by n naught dx multiplied by 0 to infinity 1 by pi n naught square root of pi n naught is, right? Yes. Any doubts? Any doubts? Any doubts? Please raise it if you have doubts, huh? Yeah. Right? So let us apply the analysis. We have seen this analysis in the past, right? Right? So x1, let x1 minus square root of e by 2 by n square root of n naught is equal to x2 minus square root of e by 2 by square root of n naught equal to z, one variable, right? As x1 or x2 tends to 0, z will tend to minus e by 2 n naught. As x1 or x2 tends to infinity, z will tend to infinity, right? Therefore we can say the probability of making correct decision, right? If I substitute these into the above equation 2, right? Substitute these together, it will be 1 by square root of pi integral minus e by 2 n naught to infinity e to the power minus z square dz whole square. Okay, so this equation you need to understand, right? If you have doubts, just raise now itself, right? So how we got this? We have substitute these as z, these as z, and both these are happening to be in z, and they are multiplied, right? They result in z, I mean square, right? So they are resulted in square. So this multiplied by this, right? Both are same. If I substitute z, it will be square. So 1 by root pi integral minus e by 2 n naught infinity e to the power minus z square dz whole square, right? So we consider this, right? So only we consider this now for the time being, 1 by square root of pi minus square root of e by 2 n naught to infinity e to the power minus z square dz. What it is, how we can write this, right? Our intention is to get in the error function form, right? ERFC form, right? So what we do, we just multiply, multiply and divide both sides here by 2 by 2 here, right? So right, so here 1 by 2, so I can say this 1 by 2, 2 by root pi. On the right hand side you can see, right? So 1 by 2, 2 by root pi, I just expand this integral minus e by 2 n naught square root of minus e by 2 n naught to infinity. I will just expand, right? Minus e by 2 n naught to 0 e to the power minus z square dz, one term, and 2 by root pi 0 to infinity, another term. Now what is this 2 by root pi 0 to infinity? this 2 by root pi 0 to infinity e to the power minus z square, we have seen in the past, this is nothing but 1. Okay, this is nothing but 1, right? So I have retained, right, I have retained this square root of, right, so 2 by root pi, right, 2 by root pi, right, integral minus e by 2 n naught to 0 as it is, right? Further what I will do, I will just bring this 1 here, right? 2 by root pi, what I'll do, minus 1, I'll just interchange the limits here, right? So 0 to minus e by 2 and not e to the power minus z square dz. And we know this ERF of minus u is nothing but minus of ERF of u. Okay, so we substitute this formula here, right? So this whole thing can be written as 1 by 2 into 1 plus ERF square root of, I mean 1 for ERF of square root of e by 2 and naught, and this whole thing can be 1 by 2 1 plus 1 minus ERFC, that is, right? So 1 plus probability of making correct decision is 1 minus 1 by 2 ERFC of e by 2 n naught. Okay, we substitute this. Now this whole thing, right, this whole thing is right sided, right? So this equation, okay, this whole part, okay, so 2 by 2 root pi, this whole thing is this. Okay, now I can write probability of making correct decision now is 1 minus half ERFC of square root of e by 2 n naught whole square. Okay, now if I expand this, what I'll have 1, right, this 2 times this, right, ERFC of square root of e by 2 n naught plus this square, right? So 1 by 4 ERFC square, right, square root of e by 2 n naught, right? So the probability of error therefore is 1 minus probability of making correct decision. 1 minus, so 1 minus this whole thing, 1 minus this whole thing is probability of error. Therefore we can write probability of error is nothing but ERFC of square root of e by 2 n naught, right? Probability of error is nothing but ERFC square root of 2 by square root of e by 2 n naught minus 1 by 4 ERFC square, right, into ERFC square root of e by 2 n naught. Now for this ratio e by 2 n naught much greater than 1, so this will be very small. This will be very small and can be ignored, right? So we can ignore the second term in the equation 8. So we can say the probability of error can be approximately equal to ERFC of square root of e by 2 n naught in QPSK. Okay, probability of error is ERFC, right, e by 2 n naught. Now what is E? E is nothing but, so before that we'll see E is nothing but the energy per symbol, right? So now equation 9 is average probability of error. Now assuming the symbols emitted by the source are equiprobable. If the symbols are equiprobable, probability of 0 0 equal to probability of 0 1 equal to probability of 1 0 equal to probability of 1 1, that will be nothing but 1 by 4. If the symbols are equiprobable, average probability of error can be written as ERFC of square root of e by 2 n naught. Okay, right? So there are 2 bits per symbol, right? 2 bits per symbol. So this means the transmitted energy per symbol is twice the signal energy per bit. Okay, twice the signal energy per bit, or we can say E equal to 2EB, and we can say now if you substitute this E as 2EB, we can say the probability of error in QPSK is, right, in QPSK is EB by n naught. Probability of error is approximately equal to ERFC of square root of EB by n naught. Okay, so this is what is the performance of the QPSK system. We can evaluate the QPSK system by means of its probability of error. So probability of error is nothing but error function, is ERFC of square root of EB by n naught. Now this So what is the probability of error in BPSK? 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 Come on. Coherent BPSK.
Sir, it's half of what we got here. Half ERFC into root of EB by 2n1.
Yeah. Then what about the probability of error in QPSK now? Probability of error in QPSK now is same, no? Probability of error in QPSK is ERFC EB by N naught, right? Right. Now, what is the difference? Probability of error in BPSK is half times ERFC or square root of EB by N naught, right? Yes or no? Whereas probability of error in QPSK is square root of EB by N naught. Okay, square root of EB by N naught, right? Yes or no? Yeah. Fine. Any
Can you go
doubts?
to the previous slide once?
Yes. Yeah. Who has raised it? Any doubts?
No, sir. Just wanted to check. Got it.
Go through. Go through.
Yes.
Yeah. So I will just stop here. Okay. I'll just stop here and continue in the next class from non-coherent modulation scheme. Okay. Non-coherent modulation scheme. So what do you think the difference between the coherent and non-coherent modulation scheme? In the coherent scheme, we have carrier as a reference at the receiver, right? In non-coherent scheme, we do not use carrier as a reference. We do not use a local oscillator there or local carrier there. Okay, we do not go for it, right? So in this case, you can see the coherent, right? So what you observe is if you go for bank of correlators or correlator circuit, it is completely a coherent detection, isn't it? If you see the correlators at the receiver, right? If you see the correlators at the receiver, it is coherent detection. And if you see the matched filters at the receiver, it is, right? It is, can you tell me, Yuvraj, what it will be? If you see the matched filter at the receiver, it will be non-coherent detection. Okay, so with keeping this in mind, we will proceed in the next proceed for non-coherent modulation schemes in the next class. Okay, any doubts so far we have discussed? Any doubts you have? Hello, Ashwin. Yeah, Kritik. Pavan. Adarsh Ashok.
No, sir, no doubts.
I'll just stop the recording now. Okay. Okay. So if you have doubts, you raise it now. We have 5 more minutes left. Otherwise, you can even drop a message in a group or in Teams itself. Once I open it, I'll just go through and I will answer to your doubts. Okay. And as I have sent, I have uploaded the material for QPSK and other modulation techniques also. Just check whether you are able to access it, Yuvraj. Can you check? Yeah, Adarsh Ashok, just check whether you
Yes,
are
sir,
able
I'm
to.
checking.
Yeah. Even one file I have put problems on PCM and all. Just
Got
check.
it, sir. It's there.
It is there, no? Okay.
Yes, sir. Yes, sir. It's there.
Yeah, fine. Okay. So we'll meet on Thursday. Okay. All the best. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah.
Thank you, sir.